Stress-strain diagrams are essential for understanding how materials behave under various loads, revealing key properties like elasticity, strength, and toughness. These diagrams offer valuable insights into material selection and design, making them indispensable for engineers in fields like aerospace, manufacturing, and construction. Before we dive deeply into stress-strain diagrams, let's quickly define what stress and strain are so we are on the same page. Stress can be defined as the intensity of force over the cross-sectional area of a material. There are different types of stress. For example, normal stress. Normal stress occurs when a material experiences axial loads where force is applied perpendicular to the cross-sectional area. It is denoted by the Greek letter sigma. Another type of stress is shear stresses. Shear stress occurs when forces or their components are parallel to the cross-sectional area of a material. Shear stress is typically denoted by the Greek letter tau. Strain is a measure of the deformation of a material. Like stress, strain comes in various forms. For instance, normal strain is the deformation experienced by a member under axial loading. This strain is expressed as the change in length per unit length. Shear strain refers to deformation caused by transverse forces. For the purpose of studying stress-strain diagrams, we will focus on normal stress and normal strain. To understand stress-strain diagrams, let's consider an example. Imagine a member with a length L and cross-section area A. If you apply an axial force, the member will elongate. Plotting the magnitude of force P against the elongation will give you a force elongation diagram. While this is useful for analyzing this specific member, it doesn't work for members made from the same material but with different dimensions. For instance, if the elongation is the same in a member with twice the cross-sectional area, the force required to achieve that elongation would be also twice. Similarly, if you have a member twice as long as the original member under the same force, the elongation would be twice the original amount. Although the force, area, length, and elongation differ between these cases, the stress and strain calculated for all these cases would be the same. If we reapply the data in terms of stress and strain, we obtain the diagram that applies to any of these members. This type of diagram is called stress-strain diagram and can show us how materials behave while displaying important material properties. To generate a stress-strain diagram for a material, scientists use a method called the Uniaxial tensile test. In this test, a specimen shaped like a dog bone is subjected to axial forces, and the elongation is recorded for each applied force. By applying the equations for stress and strain, a stress-strain diagram can be plotted for that material. Let's examine some important properties revealed by stress-strain diagrams, which help illustrate their importance in engineering. The first thing to note in these diagrams is the different regions under the curve. Typically, there are two main regions. First, the elastic region. This region ends at a point where the curve starts to deviate from straight line. In the elastic region, any deformation is temporary, meaning that once the load is removed, the material returns to its original shape with no permanent deformation. The linear relationship between stress and strain in that region is described by Hooke's law, where E is Young's modulus, a parameter representing the stiffness of material with units in Pascal. It's a crucial property in engineering used in many equations and design calculations. The second region is the plastic region. Beyond the elastic limit lies the plastic region where deformations are permanent. If you remove the load, the material will not return to its original shape. In this region, some key points to note include the yield point. Beyond this point, many materials experience a rapid increase in strain without a corresponding increase in stress. This is why the yield strength is a crucial material property. The yield point is often determined using the 0.2% offset method, where a line with a slope equal to Young's modulus is drawn starting at 0.002 strain. The yield point is where this line intersects the stress-strain curve. Another important point to note is the ultimate tensile stress point. This is the maximum stress the material can withstand. After this point, ductile materials usually experience a reduction in stress, leading to eventually fracture. For brittle materials, this point coincides with the point of fracture. Now that we know the general properties and key points on stress-strain curve, we can compare different stress-strain curves for various materials. Looking at this plot, one can notice that A has the highest slope in the linear region. This means that this material is the most resilient to stretching, making it the stiffest material. Also, if we look at B, we can see that B has the most area under the curve. This means that it absorbs most energy before breaking, making it the toughest material. We can also see that it extends the furthest horizontally, making it the most ductile material. If we look at C, we can see that this material extends the least along the strain axis, which makes it the most brittle material. Finally, if we look at D, we can see that this material extends the furthest along the stress axis, making it the strongest material, which means more force needed to break it. And this was it regarding stress-strain curves. If you found this video helpful, please like and subscribe for more similar videos and tutorials.